I am Barry Duggan, going to present a file transfer using Packet and BPSK system and sort of describe some of the development of that package. At the end of the BPSK tutorial is this flow graph, and it shows a random source feeding a BPSK modulator, channel module, and then into a clock sync and Costa's loop, traditional BPSK decoding, and then running that through a binary slicer. So at this point, we have a bit stream that is the same as the transmitted stream from the random source. So if we take that random source signal and unpack it into bits and change it to float and delay it, we can compare that signal with the received signal and show that they're the same when the delay is adjusted. And the reason for the delay is all of these blocks through the transmit and receive chain introduce delay. So we have to delay the transmit signal by the same amount to compare the two. And it works. But that is a bit stream. So after that tutorial came out, we started getting questions on matrix chat where the user would put a file source in place of the random source, pack the bits on the receive side, and feed them into a file sync and say, why didn't that work? Well, there are several reasons it doesn't work. The receive signal is a bit stream. So when you do an unpacked to packed, you can put 8 bits into a byte, but there's no byte alignment for those bits. There's a 1 in 8 chance that you'll get it right. But even if you did, the receiver doesn't have time to synchronize on the signal before the data arrives. So you'd still miss part of the data. So that's not a working solution. So the objectives of my project are to send a file without repeating it, use packet formatting to get the byte alignment, use BPSK, and provide a means for the receiver to synchronize with the BPSK before the file is sent. So there is a tutorial on this package in our wiki. It's called File Transfer Using Packet and BPSK. And there's open code in my repository under GRControl. So along the way, I wrote another tutorial for packet processing. And in this approach, I had a file source feeding a stream to tag stream and CRC, protocol formatter, and so forth. The protocol formatter uses a header format default, which includes an access key and packet length key twice. Now the problem with this, it worked, but had to pre-process the input file, because if this input file was not a multiple of the packet length, then the leftover part of the file would be hanging in this stream to tag stream buffer, waiting for the rest of the packet. And this particular one was set up for a packet length of 252. So if I preprocessed this file, I could pad it out to multiples of 252, and this would work, but that's not a very good approach. So I came up with this. I have a embedded Python block, which I will describe in detail in a minute, feeding a CRC, the protocol formatter, same header format default with the access key. And at this point, the output of the CRC32 is the payload. So by combining the header and the payload in a mux, we get what we want to transmit. Feed that into a BPSK constellation modulator, and then resample the signal to a rate of 768K, which is what I use for all of the modules in my GR control package, and feed that to the transmitter. And then to get a picture of what's going on, take this transmit signal, unpack the bits, change it to float, and feed it to a time sync. Now let's look at the embedded Python block. It takes the place of a file source block, a stream to tagged stream block, and parts of a burst shaper block. So it does the following things. It sends a preamble to allow the receiver to synchronize. It reads the file in packet length chunks and then converts those chunks to base 64 so I can send any file type with no problems. Base 64 produces 4 bytes of output for every 3 bytes of input, and it's in ASCII code. So then I send each base 64 chunk with a revised packet length tag. And then at the end of the file, send a post-file filler to assure that any buffers have been flushed along the way. Let's look a little code here. And this is just snippets of the Python. The preamble consists of a %. These are in decimal. Capital U, which in hex is 55, which gives us alternating 1 and 0 bits, and then followed by a right bracket, which one of these things. And the reason for the choice of the % and the right bracket is those characters do not appear in the base 64 alphabet, so this preamble is easy to sort out when I'm looking through the data. So the code gets the length of this packet and builds a tag. The key is packet length. The value is the length of the packet. And then I create a tag to put into the stream with that key and value, and then advance the index so that the next tag will appear at the right place in the stream. Now this is the part that reads the file. While it's not in the file, it's going to read a chunk into a buffer and then look at the length of that. If the length is 0, then it is the end of file. and close out this part. And if there's data, convert it to base 64 and then recalculate the length of that chunk. So let's look at the receive side. We receive it at 768K and then convert it down to 48K. And then this is using a symbol sync rather than a polyphase clock sync. And the symbol sync needs a normalized signal. So I added an AGC to make sure that we had a good signal and feed that into a frequency lock loop band edge detector to do the fine tuning of the signal, because over the air 2 US RPs are not going to have exactly the same frequency. And then the symbol sync, the Costas loop, traditional BPSK decoding, constellation decoder, differential decoder, and a map. So at this point, this is the received bit stream. The correlate access code is looking for that access code that we put in to the protocol header. When it finds it, then it extracts the packet length and creates a tagged stream for the output. So, and this is bit stream. So we repack those into bytes, which are aligned with the real data. Do a check on the CRC and feed that into a file sync. And then we have 4 GUIs for this. We have a frequency sync, constellation sync, input to the correlate access code, and the output to the correlate access code. And this system always puts the received file into a name output.temp, and I'll show what we do to that later. I'm going to show a simulation of the packet transmit and packet receive. So the packet transmit program sends data to a channel loopback where we can introduce some impairments, and then to the packet receive. So this is 3 separate processes running concurrently. So if we look at the first here, we'll do a channel loopback. And it will allow some impairments like timing offset. So let's put a little of that in there. And some noise. And some frequency offset. So then when we look at the received signal, we can see it converge on the BPSK. So the second process is the receive. And we'll do first we'll remove the output files. So we'll make sure we're starting clean here. And then we'll do the receive. And we've got a frequency plot, a constellation plot, the input to the correlate access code signal, and the output of the correlate access code block. and then we'll start the transmit side. So once I start this, watch over here for the constellation and you'll see it converge. It converges pretty quickly. And this is the data being sent, and then the preamble filler packets. So it is finished. So we'll kill the transmit, we'll kill the receive, and we can kill the loopback too for that matter. And let's look at some files here. So the output temp is the received file that we got. So that's the preamble, the data, and the preamble filler blocks. So we're going to run the strip on the receive side. Oh, first we're going to look at the output with ghex. So let's do that. Bang. 3. And here are the preamble packets. Up to 64 of them. There's the base 64 data. And there's the preamble filler packets. And the first one of those has the file name that was transmitted. So now if we run the strip preamble program, it will take away the preamble, the preamble, and convert the file back to its original form from the base 64. And you can see that we got output.ping from that. And if we click on that, there is our icon. For the over-the-air testing, I'll be using 2 computers. The Lenovo, which is where we did the simulation test. It will run packet transmit receive switch, which is a control for the USRP. And then it will run the packet receive. Now the way that works is the USRP is going to transmit at 432.2 megahertz to a fun cube that's plugged into my laptop. And then the laptop will send the received signal over a ZMQ pub and sub link back to the Lenovo. And the reason for this setup is so that all of the GUIs can be on one computer so I can show you better what's happening. On the laptop, the FunCube flow graph is pretty simple. It's a FunCube dongle Pro Plus feeding a resampler to change the sample rate of the FunCube at 192 kilohertz up to 768 kilohertz, which is what I use for all the modules in my repo. And since it's between 2 different computers, I have to use a full IP address and using a port number of 49221. Now to do this, I need several different tasks running. So we'll get the first one. since I don't have a Raspberry Pi running right now, I have a dummy for it because the transmit receive switch needs to control the relays. So what I will do is start this dummy Python program. And then the next task, I'll start the transmit receive switch. And we'll set the receive gain down to nothing because we're not using it, and set the frequency to 432.2 E6, which is in the 70 centimeter band, and that's also an ISM band. So for the receive, let me get this, yeah. Here are the output files from a previous trial run. So I'm going to delete those. And then I'm going to run the packet receive. And like the simulation, I've got the receive signal, the constellation plot, correlate input and correlate output. The fun cube does have a DC spike in it, but it doesn't seem to bother anything. So on the transmit side, before I can actually transmit, I have to switch the switch to the transmit mode. And then I can do packet transmit. Now watch the constellation sync over here when I start to transmit. It converges very quickly. And here's the data going by. And that's the preamble filler. So the file is done. So I'll stop transmitting, stop the transmitter, stop the receiver. And then let's go back to the receive. And we have a output.temp. And I won't do the G-hex again, but it looks the same as the simulation. So next I'll do a strip preamble. And there's the PNG file. If I click on that, there is the icon. So where do we go from here? It would be nice to integrate the strip preamble so it doesn't have to be done as a separate step. It can either occur in stream or in PDUs. And I'm still working on trying to get that to go. If I captured the file name on the receive side and renamed output.temp, that would be great. And I've looked into adding forward error correction, but haven't done enough experimenting with that to see if that really works. As far as integrating the strip preamble with a PDU, the same receive packet program flow graph. Take the tag stream to PDU and then write an embedded Python block to decode the packet and then put it back into a tag stream and put it into the file sync. So this embedded Python block would strip the preamble, convert the text packets from base 64 back to the original form, and then strip the postamble filler packets. So only the transmitted file would appear in the output file. That would be neat. As far as using forward error correction, I've tried a little bit of it, but haven't done really enough experimenting to see if it is effective in correcting errors. So those are the things that can be done. And so you are certainly welcome to clone the file and do your own work on it or fork it. Thank you.